podeliš svoju prezentaciju.
Okay.
Dear colleagues, dear ladies and gentlemen, organizers are glad to introduce you this session and our special guest chair, Professor Miroslav Mičić. And now we would like to ask Professor Miroslav Mičić to take over the conference and lead this session. Miroslav, you are welcome.
Hi, hello everyone. I would like to open the first session on the cosmology for today. And we don't have all the speakers right now, but the important thing is we have the first two. So the first speaker is Professor Srđan Samurović. So Srđane, please, if you would like to start.
Thank you, Miroslav. Hello everyone. First of all, I would like to thank the organizers for their kind invitation to participate in this conference with this talk. As you see, I will present a talk about the centenary of the Jeans equations and one possible application, which is dark matter in massive early type galaxies. This is not, strictly speaking, a historical review, although some historical references will be given in the talk. So this is just a brief overview. First, I will make some introduction regarding the whole story about the Jeans equations. Then I will present some theoretical and observational foundation for this equation. I will move to some results. First, results related to integrated stellar spectra. Then results related to various tracers of the gravitational potential. And finally, I will present some brief conclusions regarding the Jeans equations and application, in this case, of massive early type galaxies. So dark matter problem is a serious problem in modern cosmology, modern astronomy, modern astrophysics. It is still, of course, unsolved. And the question is when it will be finally resolved. We all know in the study of dark matter, we studied the contribution of an unseen matter to the total dynamical mass, and we study this problem in all morphological types of galaxies. The study of dark matter essentially began with the study of spiral galaxies. First, rotation curves were analyzed, and a lot of these curves and their behavior showed that dark matter must be present in them. I will only here mention briefly things survey used recently in the work of our colleague Milana Ivanović. She will present her talk later this afternoon. So dark matter in spiral galaxies is assumed to be a rather well studied and well understood problem. But the situation regarding dark matter in early type galaxies, which are ellipticals and lenticulars, is not so clear. This problem is less studied, and there are several reasons for this. First, there is a lack of cool gas in early type galaxies, so we cannot obtain rotation curves to study dark matter in them. Then another serious problem is related to their brightness. Early type galaxies are very faint in their outer parts, so we need very long exposures to obtain high quality spectra. Then there is another serious problem, and this is the problem of our knowledge about shape of orbits in these galaxies. And this leads to the well-known mass anisotropy degeneracy. I will say a few words about this later. I summarized in my publication in 2007 studies of dark matter in early type galaxies, and I will mention here just briefly some of the main approaches. First of all, we have to deal with integrated stellar spectra, which means we deal with long slit spectra and integral field spectroscopy, integral field spectra. Then we can use at larger distances from the center of given galaxy, we can use kinematics of various tracers such as planetary nebulae and globular clusters to estimate their total dynamical mass. And of course, we can study X-rays in early type galaxies in the objects that possess them. Then we can also analyze gravitational lensing in early type galaxies. And finally, I mentioned here the study of stellar shells. This is work done by Michal Bilek in a lot of his papers. He spoke yesterday briefly about this. So now we come to James Jeans. James Jeans introduced his equations in a series of papers starting from 1915 and 1916, and then in 1919 he published a book, Problems of Cosmogony and Stellar Dynamics, in which he summed up his results. This book, published by the Cambridge University Press, is available now. It's freely available at this site, archive.org. And Cambridge decided to do the reprint in 2009. And as you see, for some reason, they changed the front page, the title of the book, and they called it now Problems of Cosmology and Stellar Dynamics. The book is a reprinted book, is completely same as the original one, but for some reason, as I say, they changed the title. Jeans equations, however, were previously derived in 1867 by James Clerk Maxwell, one of the biggest names in the history of physics, of course. But he already had a set of equations named after him. So when we speak of the Jeans equations, we should have in mind that essentially the work of Maxwell is behind it, that he devised a set of equations which Jeans applied to stellar systems. Here is what Jeans said in his book. He said, it now appears that for our present universe, and when he says present universe, he means Milky Way, because it was at that time, 100 years ago, it was usual to call this present universe. That the problem of stellar dynamics is the same as the problem of the kinetic theory of gases, with collisions left out. This being so, stellar dynamics is naturally very much simpler than gas dynamics. So essentially here, Jeans acknowledges the work of Maxwell and applies it to the field of stellar dynamics. And now we come to year 1982 and the work of Annan, in which he presents concise history of the Jeans equation, and he calls his work Vassov equation. At the beginning of the 1980s, there appeared several works by the Japanese authors who called this Jeans equation Vassov equation. Vassov equation coming from plasma physics. And so Annan decided to list all the possible names, and here is what he suggested. He suggested 7 names, essentially, for the Jeans equation. First, Liouville equation, then Boltzmann equation, then collisionless Boltzmann equation, Liouville-Boltzmann equation, Jeans equation, equation in continuity, and finally Vassov equation. His preferred name is collisionless Boltzmann equation because, as we will see, this term is missing from the Jeans equation. And he suggested in his paper, and I quote, "I therefore end with a plea that astronomers and hopefully also physicists agree on collisionless Boltzmann equation as the proper name for equation 1, which is essentially the Jeans equation." His plea here didn't find didn't find people who will apply it in practice. So it was just this. It remained a plea, and what is now called Jeans equation is called Jeans equation. In 2017, Robson, with his collaborators, suggested that on the 150th anniversary of the Maxwell paper, he suggested that the name of the equations devised by Maxwell in 1867 should be Maxwell's others equations. So with this, he wants to distinguish the work of Maxwell in this field with his fundamental work related to electromagnetism. And now we come to the Jeans equations. Here are some basic things which needs to be said at the very beginning. That an elliptical galaxy is a collisionless system made of several billion stars, and that when we deal with these stars, we operate in the six-dimensional phase space. Volume around the position determined with x and position x and velocity v. We need to define the distribution function, non-negative function f, and this quantity given here at time t determines the probability that a given star has phase space coordinates in this given range. So we assume that all stars are identical, and we use the definition of the distribution function f. We have this following normalization, and we have the integral over the whole phase space. The function f evolves, so the probability must be conserved, and this is what is given with the continuity relation, which describes this conservation of fluid mass. The expression is given here. Rho is, of course, density, and x dot is velocity of the fluid. So we have conservation probability. These are Cartesian coordinates given here. Then we use Hamilton's equation to eliminate W dot, and we get this collisionless Boltzmann equation. Here now Q and P are generalized coordinates and generalized momentum. We have these standard equations. H is Hamiltonian and F is gravitational potential. Now we have the collisionless Boltzmann equation. This is equation 1, and this is the equation that Anon referred to in his paper when he reviewed the names for the Jeans equation. And this equation can be written for different coordinate systems, and it can be shown that no additional terms are needed in the case of ellipticals. So when we speak of the problem of dark matter in early type galaxies, we need to make some link between theoretical expressions and observables. Without theoretical concepts and what we observe using photometry, spectra, and so on. We have the probability per unit volume of finding a given star at a given position, regardless of its velocity. This is the expression. And then if we multiply this probability by the total number of stars in the population, and we get number density of stars in the real space. This is the expression. And for stars, this nu can be obtained using luminosity density, where L capital is luminosity of the stellar population. Now, in a given galaxy, early type galaxy, we cannot resolve individual star. So we must deal with integrated stellar light. And this represents the average of the stellar properties of numerous unresolved stars that lie along each line of sight that we observe. Now we define line of sight velocity distribution. This F capital, this is a fraction of stars contributing to the spectrum of the galaxy, which have line of sight velocities between this small range, and it is given by this expression. So now when we have line of sight velocity distribution, we can assume that it has the Gaussian form, at least to a first approximation. So we have simplest properties of line of sight velocity distribution: its mean value, its dispersion, and now we can use more sophisticated models of the line of sight velocity distribution, which is to model this distribution as a truncated Gauss-Hermite series, which means we have Gaussian multiplied with this polynomial, where W is given with this expression, and H3 and H4, although we can use higher numbers also, determine asymmetric and symmetric departures from the Gaussian. So now we can estimate line of sight velocity distribution. We can vary velocity dispersion H3 and H4 until the convolution of this function and some given best template best reproduces the observed galaxy spectrum. If line of sight velocity distribution is close to Gaussian, then this V and sigma will be approximately equal to V line of sight and sigma line of sight. So we managed to make the connection between the observables and the theory. So this is one example. Galaxy NGC 4473 is given above. Below is a template star. You can see immediately two effects that the spectrum of the galaxy is broadened and red shifted. And this is standard procedure to use template stars to obtain the best results. So we have two anisotropic cases. One is when H4 is negative, which means tangential orbits dominate, and we have H4 positive, that means radial orbits dominate. And this is important because H4 parameter is here a key player, because the excess of tangential motion can mimic the existence of dark matter halos. For example, you may not have dark matter, but you can have this sort of anisotropies. Now, this is a plot which shows the departures of Gaussian for different values of H3 and H4. I will just note here negative H4 when we have this flat top, and we have here when H4 is positive, we have this peaked top here. This is important for the early type galaxies, especially for ellipticals, because as you see in this plot, for ellipticals given with this red curve, H4 has positive values. Now we can finally have some basic elements to write the Jeans equations. So we define the anisotropy parameter beta, and this is parameter equivalent to the H4 parameter. It is given with this expression. So we have several possibilities. Beta is equal to 0, this is isotropic case. Beta is positive, this is radially biased case, and beta is negative, we have tangentially based case. So now we can integrate collisionless Boltzmann equation here, and we take into account that for large velocities, this function is equal to 0, which means that there are no stars moving infinitely fast. So this is the first equation here which we write, which is the equation of continuity of probability. And we get the equation analog to Euler's field equation of fluid flow. And this is these are equation 3 and equation 4 are now called the Jeans equations. They can be written in for different coordinate systems, and this is the spherical Jeans equation. This is most frequently used form of this equation used in the analysis of dark matter. And here, you see here, it's a radial component of velocity dispersion. We have beta, we have alpha. I will tell you something about this now, and acceleration, which is put here n, which determines the Newtonian acceleration, and it depends on total mass within radius r. I put this in red because you can put also some different expressions, for example, in Mond, and this is a proof of true versatility of the Jeans equations. Alpha parameter is defined this way, and this is essentially the slope of tracer density. If we have rotational component, we need to take this into account through this expression. And so when you look into literature, after 1990, we have to wait until 1980 to find the earliest application in this paper, Duncan and Wheeler, in the analysis of M87 of the Jeans equation. Now, I will start with the results. We see here integrated stereo spectra. This is a first work based on long slick spectra in the work of Binney and collaborators. They analyzed 3 early type galaxies. out to one more or less effective radius, where one effective radius is the radius which encompasses half of the total light of the given galaxy. They used the Jeans equations to model velocity dispersion, although they didn't explicitly deal with the dark matter problem. This is the question that they posed, and this is a question: is this mass to light, is the mass to light ratio constant? If it is, then you don't need dark matter. If it isn't, some dark matter is needed. So they had their observations out to one effective radius. And they found that the observed data is consistent with constant mass to light ratio in all these three early type galaxies. The same technique was used later by van der Marel using 4 early type galaxies, again out to one effective radius, and they found that constant mass to light ratio can provide successful fits. Then we have Cinzano and van der Marel, again out to inner regions, half of the effective radius, and they found no evidence out to half effective radius of dark matter. Now observations start to move beyond one effective radius, radius out to several effective radii. For example, this paper from '95 by Carola et al. They modeled 4 early type galaxies and found that one of them must possess dark halo. 4 years later, Statler and collaborators analyzed NGC 1700 galaxy out to 4 effective radii, and they found that evidence for dark halo in these galaxies, and according to them, the strongest evidence. Then in our paper from 2005, we analyzed 4 early type galaxies out to 3 effective radii, again using Jeans equations, and we combined with the X-rays observations where it was possible, and we couldn't detect significant amounts of dark matter in these 4 early type galaxies within this uncertainty of the modeling. For example, I will show now the example of galaxy IC 14159, which was studied out of 3 effective radii. This is a major and minor axis of this galaxy. This is a very particular galaxy. It has counter-rotating core, and you see here in these outer regions, H4 parameter is positive, and we need to model these anisotropies, so we include this in corrections for the velocity and velocity dispersion. This is essentially correction for velocity dispersion, and this is important to include this. And this is an example of the Jeans modeling. In the upper panel, we see modeling using mass to light equal to 7, and in the lower panel, we see corrected values of the velocity dispersion, and now we need higher mass to light ratio, about 10. This paper by Salinas is essentially the last paper that I found dealing with early type galaxies and long slit spectra, and they found that models without dark matter provide excellent fit of the observed data. We come now to more advanced technique. It is integral field spectroscopy, new useful technique based on integrated stellar spectra. We have now larger spatial coverage, and I mentioned that there are 2 generations of integral field surveys. First, we mentioned Sauron. 25 early types galaxies were analyzed. Then Atlas. Michael Bilek mentioned yesterday Atlas also. 260 nearby early type galaxies. They calculated within one effective radius 13% median value of dark matter fraction. Then we have Khalifa survey, and I mentioned here just this paper where they found that the dark matter masses is not so certain because they have some degeneracies. Second generation of integral field surveys includes MUSE. You see here, for example of dark matter fraction, again inside one effective radius. Then we have massive survey that also analyze velocity dispersion in higher moments. Then we have SAMI galaxy survey, and all these surveys are still new. They're still producing results, and we can expect some new interesting result, because you see here they go from 1 to 2 effective radii. We hope that they will reach outer radii too. Then we mentioned manga survey as a part of SDSS. Rong, for example, used genes dynamical models and found difference between acceleration between fast and slow rotators. Then I will now show some results regarding other tracers of the gravitational potentials. They are important because they give an insight into the dark matter content beyond 2 and 3 effective radii. So we can use them together with the X-rays. Again, we apply the Jeans equation. The list of observed objects with their radial velocities are first needed, and then we plot their surface density profile to find the alpha slope, and then we estimate the beta parameter, the anisotropies. We can now calculate sigma velocity dispersion using this expression, and we also calculate anisotropy S4, which is equivalent to H4 parameter or beta parameter. This is one example of the galaxy M60. With red kinematics using integrated stereospectra, and these black dots are coming from the observations of globular clusters, and we see that inside where there is an overlap, they match pretty good. Planetary nebulae are frequently used. One of the examples is Centaurus A, NGC 5128. From 93, the research started, and then we see that there were hints for existence of dark matter halo in this galaxy. Later observations went even further, out to 15 effective radii, and it was found that dark matter is necessary, but the mass to light ratio was much lower than what was coming from X-rays, and this is interesting. Then we have this Hui paper, and then they measured this dynamical mass, which is, as we can see, much lower than the total mass estimated with the Rosat data. I had to analyze this galaxy, and I found that without dark matter, you can have good fits out to 6 effective radii, and the outermost regions beyond 10 effective radii, we need dark matter or some tangential anisotropies. Another good example is NGC 3379, and it was studied in 93 and then in 2003. This caused some big debates at the time because Romanovsky and his collaborators, they found lack of dark matter in this galaxy. Again, this galaxy was studied 2007, and this is the mass to light that they found inside 5 effective radii. Globular clusters also can be used, starting from 90. For these two galaxies from the virtual clusters, velocity dispersion profiles were flat. Then central galaxy NGC 3099, the Fornax cluster was studied. Very high mass to light ratio 79 was measured. We also studied this galaxy out to beyond essentially 3 effective radii, and found later using the Jeans equations that dark matter fully dominates in these outer regions. Then we have this galaxy M49, which showed also unmistakable evidence for massive dark halo. In our study from 2012, it was shown that Newtonian models without dark matter cannot provide fits beyond 2 effective radii. M60 was also studied, and it was found that Jeans equation beyond 3 effective radii show no need for dark matter, because if we accommodate tangential isotropies, we can get some good fits. Then there is a sample of Dyson. They analyzed early type galaxies, 15 early type galaxies, and found that fraction of dark matter within 5 effective radii increases with mass. one interesting survey was Slug's survey for 12 early type galaxies, and some of them were studied for the first time. I used 10 of them to study both Newtonian and Mond methodologies, and then I found that only one galaxy could be modeled without dark matter. Three further galaxies show an increase of the total mass to light ratio, and only one galaxy needs significant amount of dark matter even in these inner regions, and remaining 5 galaxies show significant amount of dark matter beyond 2 to 3 effective radii. For example, for this galaxy, it goes out to 127. Then in our paper by Bilek, Samurovic, and Renault from last year, we analyzed a large sample of 17 early type galaxies based on their globular clusters. And for the total sample, the median contribution of dark matter inside one effective radii and 5 effective radii, 20 and 72. And this is essentially in agreement with results that's found in the literature. The dark matter fraction of slow rotators are much higher than that of the fast rotators. For example, the fast rotators, they show dark matter fractions equal to 18 and at 1 effective radii and 69 at 5 effective radii. And slow rotators, they show dark matter fraction 40 and 88 again at 1 and 5 effective radii. So you see the difference is quite visible. Then last year, we analyzed 2 nearby early type galaxies, both fast rotators, and we established profiles of velocity dispersion in both galaxies. And I want to mention here that we used the Milankovic 1.40 meter telescope mounted in Vidovica to obtain deep photometry in both B and V bands. And we modeled, for example, this galaxy 4473 out to 12 effective radii. The other one was out to 3 effective radii, and tested several cases of anisotropy. In most cases, Newtonian models could not provide successful fit unless we introduce some dark component or some tangentially anisotropic models. So this is an example of our modeling. Constant mass to light ratio model is with this red curve, and the dark matter model is this one. Now I reach the conclusion. Last year marked 100 years of publication of the book of Sir James Jeans Problems of Cosmogony and Stereodynamics, in which he presented the equations that are now known and used as Jeans equation. We show that the Jeans equations are and remain an indispensable tool in the study of galaxies, especially in early type galaxy, and the problem of dark matter in them. The application and usage of Jeans equation in early type galaxies, especially in cases of long slits and integrated field spectra, as well as some other tracers. We discussed this. And some future work related to dark matter must include study of trends in population and kinematics beyond 2 effective radii to see what's happening in these outer regions. We need to study trends in total density profiles at large galactocentric distances, because it is there where we expect dark matter to dominate. And finally, I mentioned the contribution of Milankovic telescope, which proved very useful to obtain images which lead to crucial information regarding the stellar content inside several effective radii. This is the paper published last year in Serbian Astronomical Journal, where I put much more details regarding the history of Jeans equation and its application in the case of massive early type galaxies. Thank you very much for your attention.
Thank you, Srđane. This was a very thorough, extremely thorough overview of dark matter in early type galaxies. Are there any questions?
I can have a question.
Yes, Michal, here.
Sirion, it was nice to hear you after a long time, and it was a nice talk. It's nice review.
Thank you, Michal.
And okay, so uh, are there well, what are the future prospects of observing these global clusters? Are there any ongoing projects, or do you intend to make your own observations?
Unfortunately, we don't have plans to observe globular clusters. We plan to rely on globular clusters from various surveys because we don't have much observing time at our disposal. And as you know, what we can count on is to have some good photometry of early type galaxies, which I showed in this last slide. For example, we can go out to 12 effective radii in this case. So we plan to do this essentially what you do with your colleagues, but more concentrated on some particular cases of some interesting nearby early type ellipticals and lenticulars.
Okay. So if you have imaging, then well, maybe investigating the gravitational field using star shells might be interesting.
Yes, of course.
Because well, without spectroscopic information, I don't know about any other way to investigate the gravitational field of ellipticals than the shells.
Yes, I know. That is why I mentioned. I know you're an expert in this, and people should take into account your papers regarding these galactic shells. Yes, thank you.
We can discuss about it in private because it will go for a long time. Yes.
Okay. Okay, good to hear.
Thank you for your talk and your reply, and well, hopefully we will see us soon.
Hopefully, yes.
Thank you.
Thanks.
Any other questions? If there are no other questions, we are kind of already breaking the time. Our next speaker is Marko Simarovic. Marko, please.
Can you hear me?
Yeah.
I cannot share. Okay, good. Yeah. So, can you see the screen? It is okay.
Yeah, perfect.
Okay, perfect. Okay, thank you. So of course, thanks a lot for the invitation. I'm very happy to give this talk. It is really a great pity that we cannot do this in person, and I'm looking forward to the next edition of Serbian Astronomical Conference, which hopefully will be in much better circumstances. So today I'm going to give a very brief overview of some things that we can do in cosmology from current and future spectroscopic galaxy surveys. And in particular, I want to focus on what can be done on large scales. This is a bit opposite from what Sergio was talking about. We're focusing mainly on really studying individual galaxies and their properties. Here, I want to take a different point of view and ask what can be done studying the density fluctuations on very large scales. And this is something that was historically, of course, a very successful program. Almost everything all major discoveries, if they were not made this way, at least they were established and measured precisely this way. And so, for example, the standard cosmological lambda CDM model, where we nowadays know that we have things like some vacuum energy, which is very tiny, but it is measurable, or that we do need like some non-baryonic, or we usually call dark matter. And also maybe the biggest discovery in cosmology in the last few decades, the fact that we do require some very special initial conditions for our universe to look as it looks, and therefore we need some even earlier phase before the standard, what was usually called standard hot Big Bang cosmology. All the discoveries, I think, and the detailed measurements that we're following came from this study of large-scale density fluctuations. So why cosmology can do such things? Why we can discover things which are very like tiny, like a very little, for example, very small amount of vacuum energy, which would be impossible to do in a laboratory? Well, the reason is that we are observing huge volumes. So this volume factor always plays an important role. And on the other hand, why can we discover things like, for example, dark matter? Well, because you can think about the universe and its evolution as basically like a box where you go through all possible different energy scales, and if you have any stable relic that will survive in the long run, then you'll be left over with something at the end of the day. And we have baryons from the early universe, we have neutrinos, and dark matter particles are another example of this relic. And again, it is not for the first time that we have this. It's not for the first time that we are seeing, for example, this kind of weakly interacting particles on the sky. For example, if you just remember, the helium was discovered the same way. It was discovered in the sun and not in the Earth. And again, like large volume and abundance of dark matter in space compared to this abundance on Earth is the reason why we can do it. And so, as I said, if you want to make a very precise measurements, for example, of the abundances of these quantities and understand how they interplay, how they like talk to each other, the best way that we have to do this is to study the density fluctuations. And the most well-known example, of course, are these density fluctuations in the cosmic microwave background radiation. I'm showing here the very famous now image of these little fluctuations by the Planck satellite. As you know, the CMB is to a very high degree uniform, and there are only tiny fluctuations of 10 to the -5 in the temperature. And then the question is, like, I think maybe you can ask, how come that why are these fluctuations so important? Well, first of all, you should understand that they have some very special properties. And the second thing is that how they evolve in time is very sensitive to various components, such as dark matter, baryons, or dark energy, and so on. And changing even a little bit these different, basically, energy components can lead to drastic changes in the way that these fluctuations will look like. Now, if you look at this map, of course, at the realization level, you may not be able to tell much. And so usually the way that we compress this information in cosmology about such kind of maps is through endpoint correlation functions. And the simple thing that you can do is just to measure the 2-point correlation function, basically averaging the product of temperatures in the pairs of points separated by the same constant theta angle, let's say, over the sky. Or you can look at its Fourier transform, which is called the power spectrum, and it's usually denoted by CL of theta when you do it like a two-dimensional sphere, which is the CMB. And so, if you now look at this power spectrum, it has a very particular shape. If I show you some map, which is some random noise, you may think even that, like, if you show you a map with the fluctuations, you may think that this is some random noise, in which case there will be a very simple white noise spectrum. But if you look at the CMB fluctuations, they exhibit these very particular features. And as I said, to have such kind of features, and I can discuss this in more length, but there will be no time, but to have such kind of features, you require some very special initial conditions. And also, it is really necessary to have things, for example, dark matter in a proper proper amount of it, and also to observe from the current point of view the CMB and see such kind of pattern. Also, dark energy is needed. And so, for example, I think that for example, these particular features in the CMB are probably our strongest evidence that dark matter exists, even though the hints of it were discovered, of course, much earlier in the galactic dynamics. So, so now, as I said, the way that the spectrum will look like is very sensitive to cosmological parameters. And there are a few kinds of cosmological parameters, basically, that enter here. So there are two parameters that determine the overall amplitude and spectral index of the initial density fluctuations, which are, we believe, set by inflation. It's a very special mechanism needed to generate proper initial conditions. And then we have some so-called shape parameters. These are omega baryon and omega cold dark matter, and they really decide like the relative heights and the positions of these characteristic peaks. And finally, of course, there is a Hubble parameter, which can be inferred basically from a joint analysis of the shape of this power spectrum, and basically how does it look like to us, which involves measuring some distances to the CMB. And when you convolve everything, but what can be done is to basically make a theoretical prediction for the CMB density fluctuations, calculate the power spectrum for whatever theory you want, and then do the MCMC analysis and discover all these cosmological parameters, measure them very precisely, given that these data points are of course very precise. And this is what is done to basically measure the cosmological parameters, for instance, in the lambda CDM cosmology. And this works very well, even when cross-checked with other observables in the CMB. So now you may say, well, we already did all these interesting things. So what is next for cosmology? Well, there are many other things that we can do looking at the sky, which we cannot do in the laboratory. For one typical example is measuring the sum of neutrino masses at a precision which cannot be done in laboratory. And this is very interesting because neutrinos, as is illustrated here, their effect is such that they introduce, so what is shown here is the ratio of two point correlation functions or power spectra in the presence and the absence of neutrinos. And as you can see, they introduce some characteristic scale dependence suppression of power spectrum or suppression of density fluctuations because of their free streaming. And measuring the amplitude of this suppression, you can basically measure the total sum of neutrino masses. And the future galaxy surveys will be precise enough to do this. So this is something very interesting, again, that we can say something about something so subtle as a tiny neutrino mass looking at the distribution of galaxies. Of course, there's plenty of things to learn about this very early phase that I mentioned, inflation, and this involves various things like non-Gaussianities, measuring better Slavov parameters, spectral index running, etc. Maybe there are surprises like additional energy components or long-range interactions. And cosmology is the place to look for those. There's a range of things that you can think about which will fall in this category. And also, we can also look at the early universe and we possibly find some surprises there. So, so far, we have been mainly working with the CMB. The cosmology was the main driving force because it is a very, how should I say? It is a rather clean observable, and also it is relatively easy to make theoretical predictions for how these CMB fluctuations evolve and what kind of power spectrum you can get given your theory. But as we move forward, I think that big galaxy surveys are going to become increasingly more important in this context. And so the reason, of course, is that if you look at this illustration here, the CMB is just some two-dimensional sphere. So basically, as you observe the universe in the light cone, you intersect three-dimensional space with a particular moment in time, and you get a two-dimensional sphere. And so the number of pixels on the sky, or like Fourier modes, if you want, the sphere is much smaller than, for example, the number of the pixels that you can make inside the sphere, okay? And so even very, very pessimistically, basically the resolution of maps that we can do using the full volume is much higher than if you use galaxies inside the observable universe, rather than just focusing on the CMB, which basically is on the sphere. And this large amount of information, in principle, has a potential to lead to better constraints on cosmological parameters, and then therefore, more importantly, to like maybe even possibly new discoveries. And so I'm showing here something that already exists. So for example, all these different galaxies of different types are already observed. So these are all surveys which are finished. And you can see that there is a part of this observable volume taken into account, but much more is coming in the future. And it will be very interesting to see how things will go. And I will say a few words about it. So now one key aspect, of course, here is to be able to predict the statistical properties of these maps. So you're going to observe a lot of galaxies. We're talking about billions of galaxies eventually. And you're going to have very nice maps of the universe, which have this like kind of web structure, which is called cosmic web. And for example, what is shown here is one slice of an n-body simulation where we focus, for example, on some particular dark matter halos. So these are some dark matter halos in real space, and this is how the map of this single slice in the simulation looks like. And the question is, like, you see, look, in order to really measure any cosmological parameters or discover new phenomena or new physics or new interactions or whatever you're looking for, you really have to be able to predict these maps. And predict their statistics and their properties, okay? So, of course, one way to do this is to really run n-body simulations for every cosmology that comes to your mind. But this is difficult because, as we heard yesterday, even running a simulation to really reproduce all observable properties is difficult because there are various scales which are coupled to each other, and you cannot do simultaneously large volumes and high resolution, and also it is very expensive to do it for every cosmology. So another way that people have been using for a long time, and it seems to be working rather well, is rather than really solving these things numerically, to try to understand how far can we go, like basically doing things analytically. Or in other words, the idea is that on large scales, the density fluctuations are small, and there is a hope that their evolution can be treated perturbatively. And so this is what is called perturbation theory approach for large-scale structure, galaxy clustering. And they're basically, I'm not going to go into the details because it's become very technical, but the key idea here is that as long as you're talking about some interactions of various Fourier modes, which all have large wavelengths, then their interactions are fixed by symmetries and by dynamics, so by gravitational dynamics and so on. So that is a part that you can really perturbatively write down, and you can trust. And then there is a part of the calculation, and this is, I think, more modern insight, which is very important. A part of this calculation also comes, and it has to do with this fact that long wavelength fluctuations and short wavelength fluctuations are coupled to each other, and they talk to each other, okay? So if you're aiming to describe, for example, the long distance fluctuations in the maps and their properties, you have to take into account the way that short wavelength fluctuations can cause some effects. And yesterday we had a couple of talks about galaxy simulations where it was clear that these things are happening. Now, at first sight, it may seem that this is a very complicated problem, but as it often happens in physics, in fact, it is not so complicated. And the reason is that when you are studying long-distance physics, the way that short-scale fluctuations enter is always through some effective terms, which are dictated by symmetry. So in fact, if you ask yourself, how can the short-scale physics influence long wavelength fluctuations, there are only a couple of ways, including ordinary perturbation theory, in which that can happen. And so, and these ways are fixed by symmetries, and the only thing that is then unknown is some coefficients in front of these terms. For example, if you're looking at a 2-point correlation function. And this logic is very common in physics. It goes under the name of the effective field theory approach. And this is just the same thing applied to the galaxy clustering. And so I really want to emphasize that what I'm saying is not that the universe will not look different if you change some details. For example, change the electron mass, and all of a sudden, all galaxies are going to be very different. But what is always universally the same for all these examples, that you can come up with, is that the rules in which you match, for example, the initial conditions and some final density field are always going to be the same on large scales. It is a bit like when we have some material science, and for example, we measure some elasticity, and each material we have different elasticity coefficient, which is very difficult to predict from microphysics point of view. But the fact that the force is proportional to the delta x will always be true, as long as delta x is small. And these universal relations are always correct. And here I'm arguing that the same thing happens. So the particular realization of the universe will be very different if you change the galaxy formation history or what kind of bias stresses you look at. But the rules which govern the long wavelength fluctuations are always going to be the same. And this, I think, is the main message that I want to make. Now, the question then is, how well does this calculation work? So how well does this perturbative description works? And I can show you a couple of slides to convince you that it works rather well. So for instance, here, as before, you can see the simulation. And then starting with the exact same initial conditions, you can just apply a simple formula, it's a one-line equation, to basically predict how the bias test is going to look like purely analytically, and this is what you get. So the second panel here. And as you can see, given that you're starting with the same initial conditions in both examples, you're going to get the same nonlinear density field. It looks, I mean, it's not identical, but it is very close. They're very close to each other. And just for the reference, this scale here is 20 megaparsecs. Okay? So these perturbative approaches are actually very simple, but they're very powerful because they're really able to capture the nonlinearities in the proper way. And notice that this test is much more stringent than just maybe comparing the 2-point functions of the two fields. We're really looking at the field level, and we're seeing that we're getting the same answer, which means that all correlation functions are identical. So this is something very important. And this is really interesting because it gives us confidence that our calculations make sense. Now, of course, on the other hand, people are always a bit doubtful about these things, because it is true that you make some theoretical arguments, but there will be always the question whether this really works in practice and to what extent when you talk about real galaxies. And so another piece of evidence they want to offer is the following. So given this doubts that community has, for example, we were challenged by Takahiro Nishimichi and Masahiro Takada, who prepared like a very large volume, extremely large volume, n-body simulations. These are 600 gigaparsecs cube, more than the observable universe at this redshift. But their idea was to provide some data points which are very, very precise, because the cosmic variance would be very small. And they didn't tell us how they populate. So these are galaxies in redshift space. They should resemble Bose samples, but they have centrals and satellites and so on. They didn't tell us anything about how they populate galaxies, so this we didn't know. And they didn't tell us cosmological parameters such as amplitude, omega CDM, or Hubble. And we were supposed to fit these data points and recover the unbiased cosmology. That was the challenge. And I'm showing you here the measurements of the spectra. You can see that basically you don't see the error bars by eye because they're so tiny. And on these various scales, you can see, for example, that the monopole of the power spectrum in redshift space has 0.1% error in each K beam, and the quadrupole is 1%. So these are extremely precise data. And if you have a tiny little bit of an error in your theory, you will get biased cosmology. And so luckily, so applying this perturbative techniques, we were able to recover unbiased cosmology. I'm showing you here some results of the MCNC analysis of this data. And you can see that all cosmological parameters and even nuisance parameters such as B1 are recovered in the unbiased way. And this really gives us confidence that since these volumes are much larger than current or even future galaxy surveys, it gives us confidence that we already have sufficiently good tools to make like a lot of progress and really get a reasonably good cosmological information from the large-scale structure of the universe. Now, of course, it is interesting then to ask what happens if you apply this to some real data that already exists. I already showed you the beginning, that, for example, Bose collaboration has some very nice measurements, even though the volumes and the number density of galaxies is not very high. Nevertheless, we wanted to test it to see what we get there. And we can really do the same analysis as we do for the CMP. So for example, these are the real measurements from the real galaxies in one of the data chunks of Bose. And here we can see like how these data, of course, these error bars are much larger than the simulation error bars, but we can apply the same logic. We can say, like, let me use the shape of this power spectrum in the same way as we use in the CMB. We can do like the MCMC, where we vary all cosmological parameters and nuisance parameters and feed them jointly and see what kind of cosmological constraints do we get. I want to emphasize that in this form, this hasn't been done before. And the reason is that the lack of the reliable theoretical model, and also a lot of progress that we made in this technology of really doing this calculation fast enough that we can run the MCMC analysis with them. So these are the results. So you can see that, so what is shown here is like our results for the realistic data analysis from the Bose survey. The red contours are Planck constraints on cosmological parameters. And you can focus on these blue contours, which are our Bose analysis. And of course, Planck is much more sensitive to some cosmological parameters, such as the spectral index or this little omega cold dark matter. But then some other parameters, such as the Hubble constant or capital omega matter, are measured with similar precision. And this is something that is very interesting because it means that we are already at the level where these spectroscopic surveys are good enough to, at least in some sets of cosmological parameters, they can compete with the CMB. And in the future, things are going to be much more interesting. Okay. So the reason why Planck does so much better for some of these cosmological parameters is because lambda CDM is a very constrained model. It has very few parameters, and they're all then basically nailed down by the CMB. If you allow any extension of the lambda CDM, then I think that the large-scale structure results become even more competitive. And I can just mention one thing just for the reference. For instance, like doing the analysis about the effective number of relativistic degrees of freedom in the early universe, which is usually around 3, because we're talking about 3 relativistic neutrinos. We can see that you can improve the error bar from Planck measurements and measurements of the BO scale if you add this full shape analysis. And this is one example where you can see that even though nominally large-scale structures give much bigger error bars, in combination with Planck in some models, it really helps. And there are many other examples that I don't have time to discuss. So let me finish by showing some forecasts for future surveys. So whatever I said for the simulations and whatever I said for this current data analysis, we can of course apply the same logic for upcoming spectroscopic surveys such as Euclid or DESI. And we can ask how well can we do? And this is some conservative estimates of how well can we do. So these dashed lines here, these blue dashed lines are Planck constraints, okay? So, and then maybe you can focus on the red contours, which will be the power spectrum analysis of the upcoming surveys. And you can see that already the things that are ongoing, for example, DES is already collecting data for 2 years. In a couple of years, if we have the first results, we can see that the total constraining power on most of the cosmological parameters is similar to the CMB. And in combination, so if you combine, for example, the CMB and large-scale structure, you really gain a lot for many of these things. And this is why I think this is very interesting, because either we are going to test lambda CDM to much higher precision than we do today, and everything will be fine, or we're going to start seeing some inconsistencies and cracks, and this will be a hint of something new that will be potentially very interesting and would like to discover. All right, since I'm running out of time, let me stop here and say that in conclusion, one important message is that we had a lot of discussion about simulations. They're very important for various reasons, but it turns out that if you just want to do cosmology on large scales, you can really rely a lot on these analytical modeling, which are very simple. They can be evaluated fast, and they're very general. They work for any cosmology. Those seem to be working very well for a various range of tracers and various kinds of galaxies, all kinds of redshifts, and so on. Even today, with the data that we have, we can put some meaningful constraints on cosmological parameters, which are comparable in some cases to those of the CMB. And this is going to improve quite a bit in the future. And this is why I think this is very exciting, because either we are going to really test lambda CDM at unprecedented level, or possibly discover some new things. So I will stop here, and thank you for your attention.
Thank you, Marko. So it seems that we're going to have plenty of time for questions, because our next
they're late.
Okay. Unless something changed the last couple of minutes, but last time I checked, it was a couple of minutes ago. They were not present. But in any case, okay, let's first see if there are any questions for Marko.
Can I have a question?
Of course.
Yeah, yes. So I'm Michal Bilek again, and yes, I'm not an expert on cosmology at all, but I wanted to ask if these future planned surveys will able to ask at least some of the basic questions. For example, if there is dark matter or modified gravity, or to exclude some types of dark matter, such as this interacting dark matter or warm dark matter. Yes.
Yes. So these are all very good questions. I think that, but they come at different levels. So let me maybe all the way up. So for instance, when I said that, so for example, like the reason why we think the dark matter somehow must be there, and it is not modified gravity, is exactly this figure here. Because you see, this characteristic, the so-called acoustic peaks, I mean, they originate from the fact that when you have this primordial plasma, where you have baryons and electrons, so protons, electrons, and photons all coupled together as a plasma, then there's certain sound waves in this plasma, okay, which, as you expect, there's some pressure if you compress this baryon photon fluid, and there's some longitudinal sound waves that basically propagate through this plasma. And now, if you don't have dark matter, if you just think that there are only baryons and this is all that there is, then of course the gravitational pull acting on baryons will be very different than if you have dark matter. Why? Because dark matter doesn't talk to baryons or photons or electrons. And so dark matter, if it comes in the right amount, which is 5 times more than the baryons, will basically will cluster despite all of this sound wave propagating around, and it will form potential wells which are deeper and deeper, and therefore putting more and more pressure on the baryon photon fluid. And so you see, the way that sound waves propagate and the way that these fluctuations grow in time in the early universe, which is a very simple system, it's really just simple plasma plus cold dark matter, can be described to some extent even like in terms of formulas analytically and solved in some simple case analytically. You will see that unless you put cold dark matter, you will never be able to produce such patterns. This is one thing. And the second thing is that you will never be able to grow fluctuations from this 10 to the minus 5 level to what we have today to form galaxies. So I think that this is order 1 example which shows that some kind of dark matter is really necessary. It is not enough to modify gravity, because modified gravity will not produce this effect that there is some extra clumping of something else which is causing baryons to fall in and produce these characteristic patterns. So I think that by now we do believe the dark matter is really there. We don't know what it is. Now, your second question is like, maybe it can be some kind of a not so cold dark matter. Maybe it can be some lighter particle. Not hot dark matter, no, but some warm dark matter, it is possible. It can be axions, which have very interesting structure on small scales. It can be primordial black holes. It can be very many different things, but it has to be something which doesn't interact with baryons and like interacts on gravitation. Now, for these other questions, can we say something about self-interacting dark matter? And I think that these big surveys are more aimed at making these large maps, but they don't focus too much on individual galaxies. So individual galaxies are not measured very precisely. For these questions of self-interaction, or for example, I think it is better to focus on small scales. And there are other kinds of surveys, such as LSST or like other optical surveys, which measure very carefully the details of the nearby galaxies. And I think that looking at these small scales may be better to answer these questions. For the warm dark matter, I think that the leading probe at the moment is Lyman Alpha Forest, and probably it will remain for a long time. So that will be my answer. So they can teach us something about interactions with baryons, I guess, because they will put even tighter constraints for what is possible in the early universe, just looking at the distribution of galaxies today.
Okay, thanks.
Any other questions?
Hi, I will have a question. This is Anna from Observatory in Belgrade. Do you hear me? Okay.
Yes, absolutely, please.
Oh, first, I must say that I'm not Lambda CDM believer. Also, I'm not a cosmologist, but I do read a lot about this. From what I read, this first peak does not prove anything. You can produce it without dark matter at all. Is the second peak that's important, that the lambda CDM also missed in 2000 with the boomerang experiment. So then they finally tuned the baryon fraction, and now we have the problem with the missing baryons. So what a bit bothers me here is how confident are you that the lambda CDM works, okay?
Yes, right. So I think that, yes, along the way, there was a lot of, so you're absolutely right. So I think that, well, there are many features here, which of course, as I said, like what determines this amount of dark matter and so on are the relative positions and heights of these peaks. So this is very important. And I think that it is true that you can invent examples where you can get the first acoustic peak or first bump if you want, but then having all these subsequent things which are going in exactly this way, it is very difficult without dark matter. Okay. Now regarding and boomerang, I think that boomerang, if you remember, this came the results came basically around the same time as supernovae had this hint of the dark energy, and in fact boomerang missed things like it had a very bad measurement of the second peak. So there was also confusion about whether the universe is flat or not. This was another thing that was resolved once we understood that the dark energy is really there. So I think that by now you see that it's very difficult to come up with something else, because I'm showing you here only one example. This is temperature. Now, if you measure the polarization of the CMB, then you have like two more spectra that you can do. You can do like either polarization or polarization temperature. And those are much more sensitive, for example, to velocities of this fluid and so on. So they probe different things. And so if you combine all of them, lambda CDM fits them very well. But the real difficulty is that it is close to impossible to come up with an alternative, because, and it's not a matter of just not being imaginative enough. There are really so many constraints that we can hardly do anything about it. Now, regarding the missing baryons, I think that, you see, this is a different kind of question, because the question is like missing baryons problem, I think, arises because you're trying to account for all baryons looking at small scales. You're looking at galaxies, galaxy clusters, and you're basically counting and doing some kind of accounting of all possible, how much is in the gas, how much is in the stars, how much is like here and there. And whenever we look at small scales, usually there is a chance that we can maybe misinterpret something. And I think that there was a recent, like, for example, another CMB also comes to help, because there is one of the effects of the CMB is that
just a moment, please. Zaria Lukic is here.
Oh, is here. Okay, good. So I'll stop making that.
But Marco, please continue your
yes.
answer. Just
okay, good. I think that, for example, CMB is used recently because you see, as it propagates through the intergalactic medium to us, sometimes it scatters on some free electrons, and there are effects like Sonia-Zeldovich effect, or even thermal Sonia-Zeldovich effect, kinetic Sonia-Zeldovich effect, which I think can be used to estimate how much baryons are there. And if you do this independent measurement, which doesn't come from accounting, but somehow it's a global integrated amount of baryons, then you get that amount of baryons is correct. So I think that if there is any problem, I would more think that maybe we're missing something, some observation, or there's some systematic error somewhere when we do this accounting, rather than really looking for some error in the CMB.
Okay, can I have time for another short question or not?
Sure.
Yes, you have.
Well, the Hubble constant problem, that is a huge issue. You are so confident at the value that is below 70 within the errors, and all observational evidence favor it's the value with errors above 70. So yes. What can you say about that?
Yes, you're absolutely right. This is like where is it? For example, I can use this. So it is a big issue, I think. So the question is like, so for example, this cosmological observation, if I just look at the galaxies and nothing else, I will measure again something below 70, basically is a blue contour. Planck measures again something below 70. And then there are so-called local measurements, or I would maybe more call them direct measurements, like supernovae. Mm-hmm. Or for example, another important examples are time delays, Lansing time delays, which somehow suggests that there is a higher value. I mean, there are other measurements as well, but they have much bigger error bars, and it's a bit hard to tell. So, so I think that this is very interesting. Like so far, we don't know. I mean, supernovae. Many people looked into it, and supernovae indeed, based on whatever calibration they can do, and nobody found any error in this calibration, do prefer higher value of Hubble. Regarding the time delays, many people, including myself, raised some problems with these time delay measurements, and the reanalysis of these TD Cosmo lenses recently showed that actually they're now getting something which is 67 plus minus 2 or something like that. So I think that again, the problem is that you see it is so difficult to calibrate things to 1% level in this direct distance ladder because there are many steps and it is really enough. And also, you see, there are many steps, and at the end, you have to combine many supernovae to get some smaller error bars. So you're basically counting on square root of n. So for your statistical error bar shrinks, but you're not sure if there is some systematics at this level in each individual example. And I think that given how complicated this calibration is, if you really look at the papers, they really do something which is very difficult to calibrate Cepheids, to find local supernovae, to calibrate supernovae, to go to the Hubble flow, that I would say that, for example, it was easier to spot some problem in the lenses. This was now fixed, and I think that the numbers are now coinciding with Planck's. At least there are two local measurements which disagree. So you see, and there are also tip of the red giant branch measurements, which also use Cepheids, which disagree with supernovae. So I think that small scale measurements or local measurements have this problem that calibration is very difficult. It's not that people do something wrong, it's just that maybe they're not aware of some issue, and this can easily happen. So with more data, I hope that this will be clarified. But I would say that the global measurements from the CMB or large-scale structure, I would think that they're at least simpler to do. They're much more transparent, and maybe they're wrong. I don't know, but I would bet, if I have to bet something, I would bet on that.
Okay, I wouldn't, but okay.
Okay.
Thank you.
Sure, no problem.
Okay, any other questions?
One very short comment. Yeah, so there is a new modified gravity theory which is supposedly able to fit the cosmic microwave background. I'm not an expert on morphology, so I cannot judge, but I have sent the link to the chat.
Okay, yeah, okay, I can take a look. For what I know, like looking at some of these papers, they're always focusing on I think temperature, polarization. We can cross-check if they have polarization there, but it will be some. Yeah, we can take a look, but I would be doubtful that there is a full complete model which fits everything. Okay.
Any other questions? Any other supporters of no dark matter?